Hi guys. I wanted to give you a very quick and easy introduction to just what an ECG is um, before you embark on what I think are perhaps slightly more complicated views of what it is. So you guys have seen this before. It's not new. These are action potentials that you will find in the heart in the different cells. The one that people talk about when they talk about, quote, the action potential, unquote, is usually the ventricular cell action potential. They are all different because they all have different channels in the different tissues and at different densities, and we'll cover that later. But I want to remind you that your cell starts at rest, which is about minus 80 or minus 90 millivolts. Your cell depolarizes when an action potential from the cell connected to it. So remember, cardiac cells are all connected and they propagate. And so if the cell on my left fires an action potential, it propagates to me. I fire one, and what that means is that I depolarize. My voltage shoots up to, I don't know, about plus 20, and it'll hang around somewhere around 10 millivolts or about 0. We consider this to be the cell in the depolarized state. And the cell at minus 80 is in the resting state, and then this is the repolarization phase, where after about 200 or 300 milliseconds, the voltage comes back down to rest at about minus 80. So we're going from minus 80 to depolarized, about plus 10, and then repolarized back to minus 80. All right? So this is just a quick review of how the action potential propagates around the heart. It starts in the SA node, which fires action potentials all on its own. It's found somewhere between the right atrium and the superior vena cava. It's a very small sort of area. It fires an action potential. It propagates from that area through the atria, okay? And then it hits what we call the AV node, or the atrioventricular node, and all the action potentials go through that node. There is a layer of fibrous tissue here and here, which is an insulating, here and here, which is an insulating layer. That means it does not conduct action potentials. And so the action potential can't get to the ventricle because this layer is between the ventricle, this layer here, up here, is between the ventricle and the atria. So we hit the AV node. There's a delay as the action potential very slowly propagates through that node, and then it runs like a rabbit through the Purkinje fibers out along the endocardium, okay, like this, and it spreads along the endocardium through both ventricles very quickly, and then we get a nice even propagation from inside to outside across the ventricular wall. All right, so what does this have to do with the ECG? In order to get you through that, I have to introduce you to what I call the electrical blob. The electrical blob is this square, and it represents a big cell, okay? So in the heart, this would be a bunch of connected little cardiac cells, but I prefer, at least for the purposes of an initial demonstration, to just think of it as one big blob, okay? And we have here your anode on the left-hand side, and we have the cathode, usually designated by a little plus sign there, on the right-hand side. An ECG is a measurement of what the cathode sees relative to what the anode sees, okay? And what I mean by that will become clear in a second. So right now my blob is at rest, and you know it's at rest because it's negative on the inside and relatively positive on the outside. Negative on the inside, that means for a cardiac cell about minus 80, okay? So right now both of these electrodes, the anode and the cathode, are both seeing positive charge on the outside of the cell. They cannot see what's inside, only what's outside. And right now they're seeing the same thing, positive on the outside. So what we have is a flat ECG because they're seeing the same thing. We're at baseline. Now let's take our blob and let's start a depolarization on the left side right here, okay? Now what happens is just on that side, because we haven't propagated across yet, we get an action potential that fires, and the inside of the membrane, right on that part of the cell, becomes positive. That means about, plus 10, right? Because it'll fire, it'll go to about plus 20, and then it'll come down to about plus 10 or about 0, and it'll sit there for about 200 milliseconds. So the inside of this membrane becomes about plus 10. The outside becomes negative relative to that. Okay, so what's happening here is my anode is seeing a little bit of negative charge. My cathode's still seeing a bunch of positive charge. My cathode is positive relative to my anode, and I get an upward deflection in my, quote, ECG. Okay, now the action potential propagates a little bit more here. Okay, and we get even more negative charge on the outside. And my anode sees even more negative charge relative to my cathode. My cathode is positive relative to my anode, and I get a further positive deflection on my ECG. Now my action potential propagates across the cell, and now my cathode starts to see some negative charge right here. Okay, so now my cathode's still seeing positive charge relative to my anode, but not as much. And so my deflection starts to come down a little bit, okay? And now on 4, my action potential has propagated all the way across the cell, left to right. And now I'm back down at baseline because both my cathode and my anode are seeing negative charge. They're seeing the same thing, and so I'm at baseline. And right now I want to pause, and I want to point out that right here at 0, we were seeing baseline when both of these electrodes were seeing positive charge, and we were at baseline because they were seeing the same thing. Now my cell is in a completely different state at 4, but my ECG looks exactly the same. Now my blob is completely depolarized. It's all in the plateau phase, okay? But the ECG looks the same. So remember, your ECG, it tells you about, it doesn't really tell you about the state of the cell. It only tells you about the state of the outside of the cell at one electrode relative to the other. And if both electrodes are seeing the same thing, then you're going to get a baseline recording here. And that could mean all the cells in the heart are depolarized, or it could mean that they're all at rest. But if it's all the same, the electrodes are going to see the same thing, and you'll be at baseline, okay? Now on 5, I start repolarization, and I get a negative charge inside relative to the outside because this part of the membrane here on the very far left is sitting now at about minus 80. It's come back down to rest because I'm repolarized. So now my anode's seeing some positive charge here. My cathode is negative relative to my anode, and I get a downward deflection. Okay, and now on 6, my action potential is propagated more. My anode's seeing even more positive charge. My cathode's still negative. And now I get even a further downward deflection in my ECG. And then, of course, eventually what will happen is that you'll completely repolarize the cell, and you'll end up back at 0 again, where you're back at baseline. And that will take you at about right here. As my cathode begins to see more positive charge, my deflection migrates back toward baseline, and eventually I'm back at baseline again. Okay, so that very quickly is how an ECG works, only this is in our blob. Now we're going to take our blob, and we're going to put it in the middle of the chest of this nice man. Now our anode is up here, our cathode is up here, and my depolarization is propagating from the anode to the cathode. And so you'll notice, for instance, on lead 2, which is the one that most people refer to when they talk about, quote, the ECG, my propagation is headed in this direction, and my anode, as the depolarization takes place, my anode is on the right arm up here, cathode down here, my depolarization propagating in this direction. And so when depolarization takes place here, my anode starts to see more negative charge and my cathode is seeing positive charge because all the cells in this area are still at rest. And so I get a nice big positive deflection here. The only thing I want you to notice about these other leads, Dr. Shaw will introduce you a little bit more to them. They only see the portion of the depolarization that travels along their line. So if your anode is on the right arm and your cathode is on the left arm, as in lead 1, you only see the amount of this propagation that propagates left to right. You don't see anything that propagates downward. So you notice this wave is smaller because less of this wave propagates from left to right than propagates right along lead 2. And for those of you who are familiar with the term, this has to do with the vectors, for those of you who are mathematically inclined. Okay, so that's all I want you to know about that. Also notice that if the direction of the depolarization, for instance, right now I'm going from left to right. I've changed the direction of the depolarization through the tissue here in this guy's chest. Now notice that the depolarization in lead 1 is actually going from left to right, not right to left like it was up here. And so now we get a downward deflection. So if the depolarization changes direction, the deflection changes as well. And that should make some sense to you if you think about it. So now let's look at our heart. Let's put our anode up here. Let's put our cathode down here. Okay, and let's talk about the SA node at 0 seconds. That's what the 0 stands for here. We are at the SA node. We started depolarization. The depolarization propagates, and let's say it hits about right here, my blue line. So everything to the left of this line is now depolarized, which means there's a bunch of negative charges here on the outside of the cells, positive on the inside, and we're sitting positive on this side of the line. Okay, so all the atrial tissue on this side positively charged. So my cathode is still seeing a bunch of positive charge, but now my anode is seeing negative charge because the tissue in that area is negative. And so what will happen on my ECG is I'll see a positive deflection. And most of you know now that that positive deflection actually comes out as the P wave in your ECG. Okay, and we propagate to the AV node. And eventually my atrium becomes all depolarized, all negative. You end up back at baseline. You hit the AV node. You hit what's called the AV nodal delay. Notice that we enter at 30 milliseconds, 0.03 seconds. We exit the AV node at about 160 milliseconds. So that's a 130 millisecond delay to get through this little bit of tissue. Then we propagate along the endocardium, down the septum, through the Purkinje fibers. Okay, and notice that only takes 30 milliseconds to get all the way here from the down the septum and out to the end of the endocardium, and then we propagate inside to outside, and that takes another 30 milliseconds. Okay, and so that's how our action potential propagates around the heart. And now if we look at repolarization, white is sitting at rest. We depolarize, we go down the septum, out along the endocardium here, and eventually from inside to outside, and now the black is completely depolarized. Now repolarization takes place, and repolarization starts on the outside and actually works its way in. So it works in the opposite direction of depolarization, and then back up the septum here until we end up back at rest. Okay, and that takes you through the complete depolarization and repolarization cycle. All right, and finally I want to end with this figure, which is once again demonstrating how our action potential propagates through the heart. Here are a bunch of action potentials, and they are lined up in time. So at time 0, our SA node depolarizes, and right here, this line here, pointing here, that means that's what this action potential represents. It's the SA nodal action potential. It takes place at time 0 on this time scale. And now let's look at the time scale. See our P wave here? If we look at our P wave, we can actually see that I can't draw a straight line, but that is where our atrial muscle is depolarizing. So these action potentials here and here are firing in time right where the P wave lines up. Okay, don't let my blue line fool you. I can't draw. okay? But that's the period of time they line up. Now, if we look at our QRS and we look at our ventricular depolarizations, you can see that those line up almost perfectly with the QRS. And we are depolarized at the end of our QRS because our ventricular myocytes are firing. Now we're in the plateau phase in the ventricle everywhere. The ventricle is completely depolarized. Our ECG is back at baseline, and this is called the ST segment. The PR interval is the interval between the P wave and the QRS. That's where you're in your AV node. So that's the AV nodal delay. And then finally, we get repolarization of the ventricle, and these ventricular cells repolarize, and that lines up with our T wave, okay? So the T wave is repolarization of the ventricle. That's my quick round the horn on the ECG, my easy blob introduction to it. And now I think you're ready to go into Dr. Shah's stuff and see his introduction from a clinician's point of view. Okay? Thank you.